I'm a second-year PhD candidate and working on interdisciplinary of AI in transportation. Elvin is my supervisor, as well as Winnie and Serge. So far we have heard lots about shared mobility and public transport. Let's switch to another important transportation mode, which is cycling. So we know that bicycles have multiple advantages. It's a sustainable transport mode. It's popular in the Netherlands, and it's important to know the travel time estimation so that we can plan our route. It can also help the municipality to upgrade infrastructures, also provide insight for traffic control. However, there is very, very little attention received for bicycle travel time estimation. And why we have that? Because the first challenge is from the limited availability of data sets, primarily because of privacy issues. And the second challenge arises from the diverse and complex behaviors of cyclists. I believe that many people, they would just cross when there's a red light, and also take car lanes, pedestrian lanes, right? The third challenge arises from the lack, yes, of strict road constraints. And also sometimes some people, they cycle fast, and some people, they cycle more slowly. There are already lots of models proposed for car travel time estimation, so that we will have like very advanced Google Maps route planning functions, etc. Then why don't we just apply the car traffic model methods to bicycles? First, also from the data quality, because the GPS data quality, they are incompatible. Car methods, they depend on quite good data sets, for example, like frequent sampling rates, and also high quality. And also the volatile travel times. For example, here we have a distribution that we have this kind of long tail distribution. And of course, car methods, they will not consider cycling specific travel behavior. So that's why we have this study, this research on bicycle travel time estimation. So now we were going to formulate this problem. So on the left side, it's a classical intersection. We have car lanes and cycle lanes. Considering that cyclists, they can still cycle on car lanes. So we need to consider the whole network. Then we have the OpenStreetMap. We have this line string representation because we are interested in the intersection, the correlations between different road segments. So we use a line graph, which means that we model each road segment into a node and their connections into the edges. So we can see that the graph representation is quite dense. So this is something also different for cars, because cars, they will not drive on cycle lanes. So the graph, the resulted graph is also much smaller compared to cycle network. So here, just to give a brief definition, we define a trip. So it's composed of GPS records. This is our dataset, GPS records dataset. We know at what time it has passed to which point. We also know that which road segment it has traveled. Also the traveled ratio, because you can start in the middle of a road, and the starting time. So our goal is that with all these things, knowing the starting time and the routes that the cyclist chooses, we want to estimate his travel time. Okay, and we also know the road infrastructure, of course. So on the left side, for example, we might, in our training data set, we have this trip 1, the red one. We know the second one, and what we want to estimate is the blue one. So we can see that the route chosen by the third cyclist are not traversed by the previous two. So there's also this data extrapolation problem. So here we propose a geograph-based neural networks for bicycle travel time estimation. Basically, we have first, let's look into these two main components. We have a road network learning component. So we take the whole road network as input. So here we can see this is the Rotterdam urban area. So we build a line graph as mentioned before, and we do encode, process, decoder structure. All right, and it's not enough to only consider the routing structures. We also need to combine the trip-specific perspective. So here we have a specific trip that we want to travel, a specific route, sorry. Then we can construct a trip-specific travel graph, which is a directed one. And similarly, we pass encode, process, decoder structure. So in the end, we will have a graph embedding, a node-wise embedding. So for from the infrastructure learning, the road network learning, we have like the node embedding for every road segments in the network. So we have a whole series. And then when we want to estimate for one trip, we just need to take out the traveled road segments like here, for example, and we combine them and we do some further works to estimate the likelihood of different speeds. Here, a specific cycling character is integrated because we have a speed limit for cyclists. It's not like cars. The variation could be very high. So here we the maximum cycling speed in Rotterdam urban area is below 10 meters per second. So we could discretize this speed range and come up with a speed vector. And also so in this way we can have a likelihood, like for example, 50% probability that I'm gonna cycle with the 2 meters per second. And so in this way we can derive the expected travel time for each road, and then we can combine them. So this is the whole workflow. One of the novelty of this work is that we have proposed a duograph approach that is different from traditional duograph definition. Normally, when people refer to duograph, we mean like a node graph and a line graph. So here it's different. We have two different physical meanings. One is the static road graph, so the infrastructure perspective. The other is the directed graph, which is the trip-specific perspective. And why we do this? So we can combine the perspectives, and also it's easy for parallel processing because the whole road, this network is very big. Like before, I have shown you a figure of just a single intersection with, and we have so many nodes and edges. And for the encode, process, decode structure, it's quite simple. We just use MLP for encoder and decoder, and graph neural networks for processor. And now we implement our method to a real-world scenario. So since there aren't many studies on bicycle travel time estimation, we have come up with, we selected some baseline models. There are the first two is just statistical ones, and also some simple machine learning models. And the last one is one common baseline for car travel time estimation. And here we also introduce a similar data set. It's a crowdsourced data set collected in Berlin via a mobile app. So it spans from June 2019 to January 2025. It's almost 6 years, but there are only 22K trips. Considering the whole road network, it's very sparse data set and the whole time span. And here, the road network, we have like almost 50K nodes and many edges. So this is also a real-world challenge in bicycle travel time estimation. Then we compare our performance with baseline models. This is our model called DG4B. So we can see that our models generally has lower errors compared with other ones. So here we divide different trips into 3 categories: short, medium, and long. So short ones, they are noted with the blue, and medium for green, and long for red. And on the left side, we have the error of the whole travel time estimation. On the right side, we have the error of the speed, estimated travel speed. And we can see that our model performs the best, especially for short trips. Actually, short trip travel time estimation is more challenging because for short trips, the travel time can be easily impacted by traffic signals or personal behaviors. Like suddenly I want to stop here. I don't know. While these transient factors, they can be smoothed out or averaged out for longer trips. And also we can see that steep TTE, the common baseline model for car traffic, performs very bad. This also shows that it's inappropriate to just apply car methods for bicycles. And also we have compared the performance for peak and off-peak hours. Surprisingly, we see that the performance on peak hour, so this part, the bars, they're lower than off-peak hours. One explanation might be that for peak hours, there are many cyclists. Imagine that on the road. So there is a better bicycle follow model. Like you have less freedom. Like I can just cycle very, very slow or very, very fast because there are more people. So makes it the model easier to learn this pattern. Yes, and also we tested our method on a different data set, Dutch data set. On the left side, we have the German data set that we mentioned before. So we always have these short trip categories, and the y-axis is the data error. And on the right side, we have the Dutch talking bike data set. We can see that the errors are huge for Dutch data sets, especially for short trips, the blue dots. And also there's an interesting phenomenon here, like the short trips, we can see that it occupies like almost 90% of the data set. So it also implies a data, ununiform distribution problem. So the Dutch data set has more trips, but also more data bias and errors. So then we were thinking that if there are more errors in the short trips, meaning that we also have more uncertainty on the ground truth. So why not like we just use parts of the short trips for training? So here we have the results. So the x-axis like 30, 50, 80. It means that we use 30% of the short trips combine, also medium and long trips, 50, 80 for training, and the test and validation data set remains unchanged. So we can see that, especially for this deep TTE, the car model, the variation is huge because it's normally it's a large model, so we also need more data. So like when you increase the data sets, there's a sharp change, performance change here. And also we can see that our model is generally robust to data sizes. Yes, so here, now I'm going to wrap up this presentation. There are some key takeaways. So we know that estimating bicycle travel time is hindered by limited and low quality real-world data sets. And we cannot just directly apply car-based models to bicycles. And in this presentation, we introduced the DG4B. It's a dual graph neural network for bicycle travel time estimation. And it outperforms baseline models. It's also generalizable on different cities and countries. Thank you for